Hello and welcome to this video. In this video we are going to be finishing off the topic of stationary waves. So in the first video we looked at how stationary waves are formed. So we said that it was two progressive waves with the same frequency traveling in opposite directions. They superpose and then they constructively interfere to form antinodes and destructively interfere to form nodes. Then we said that we had what we looked at and called the fundamental harmonic, or the first harmonic, and we said it looked something like this, where these points are the nodes, which we define as being the nodes are the points of zero displacement or zero amplitude, and the antinode was the point of maximum amplitude. Okay, so from there we also came up with this equation. So this is the first harmonic. So we came up with this equation that the frequency of the first harmonic is 1 over 2L root T over mu. We said 2L was there because this was the wavelength, and the root T over mu was there because the root T over mu is the speed of this wave traveling along through this specific string or wire or whatever it might be. And then we also looked at the second harmonic, which is very roughly drawn. Let me try that one again. Okay, so we'll try and make it a little bit more accurate. So let's go with that. Okay, so then these two things should be the same size. I'm just terrible at drawing things. But this is a node. This is also a node, and so is this. These points are the antinodes in the middle here. This is the second harmonic, and we said if we wanted to get the frequency of the second harmonic, we would just take the frequency of the first harmonic and times it by 2, and then we'd get the frequency of the second. We could also look at the third harmonic, which looks something like this, that then had 4 nodes and 3 antinodes. We said the way that you want to work out what the harmonic should look like, if you've been given a question that says draw the second harmonic on this string, the way you would work out how you wanted to draw that is that the number of antinodes is equal to the harmonic that you want to get, which we can see here. In the first harmonic we have 1 antinode, second harmonic we have 2 antinodes, third harmonic we have 3 antinodes. Now what we're going to go through in this video is now putting a little bit of extension on this, and what we've got, all of these stationary waves are fixed end stationary waves, meaning that we already know that the 2 points on the end always have to be nodes, because we chose the example of a guitar string where they're tied down at both ends, and so that space in the middle where they can form the stationary wave has to be between 2 nodes. Okay. We also said that this isn't always the case. We can sometimes get stationary waves that form in wind instruments, and if we think about a wind instrument like a trumpet, it has an open end. So then what would these look like? So I'm going to draw these also as the first, second and third harmonic. I'm going to get rid of this equation so I have more space. So the first harmonic, I'm just going to use this as a rough diagram of what this is going to look like. This is going to have a little bit of a slit in it from where the mouthpiece is, that's going to cause this kind of first harmonic. Okay, so this is the first harmonic. You'll notice in this case that the wavelength of this is actually going to be, if this length of the tube is L, the wavelength of this is going to be 4 times L, okay? Because we have an open end here, and so the open end can't be a fixed point in the middle. It has to be at the open end of one of these things. The second harmonic is going to look, so we're going to start from the middle. We're going to have a first half of the wave. Let me keep this consistent. And it's going to look like this, still an open end so we still have an antinode at the end of the tube. So we have an antinode at one end and a node at the other end. Okay, and the wavelength in this case is just going to be 4/3 of the length. Okay, 4/3 of the length. This is because currently we have 3/4, so the length is currently 3/4 of the wavelength, and so therefore we just have to get this 4/3 onto this side, so we get it to be 4/3 is the wavelength. Okay, now the third harmonic, you can probably see where this is going now. We're going to have 2 and then an open end. Okay, so we have an antinode at the end, we have a node at the beginning, we have a node in the 2 nodes in the middle, and we have a node here as well, and then antinodes in the middle where you have the maximum amplitude. In this case, the length is actually 1 1/4. 1 1/4 of this, so that's 5/4 of the wavelength, so therefore the wavelength is actually 4/5 of the length. Okay, so there's a specific difference between these. While both of them will form stationary waves, because we'll end up having a reflected wave at the end of this, a good question to ask, by the way, would be, how is this wave actually reflected at this open end? Surely it should travel out, and surely we hear the sound because it travels out. The reason it is actually reflected is because when we're blowing into the trumpet or the saxophone or whatever it is, it causes a massive difference in the air pressure of whatever air is in front of this, and that air pressure is what actually causes that sound wave to reflect back. Okay, so the reason it reflects is because of the pressure in the air here, and all sound is a difference in the air pressure. And so because we've changed the air pressure here, the sound gets reflected back into the tube. Now we could keep going with this. You'll notice that the one tip that I had in order to notice whether it's going to be or how to draw these harmonics. So the first harmonic was because it had one antinode. Doesn't work. Sorry, it still does work for these as well, because we still have first harmonic with one antinode at the end. Second harmonic still has 2 antinodes here. Third harmonic still has 3 antinodes. But the frequency of these things, the equation for that is going to be much different. Okay, for that reason, they don't ask you to work out the frequency of these. If they do, they'll give you one of them and they can ask you to work out the others. They'll usually give you the first one, in which we know the relationship. It will still be the same. That if this is frequency 1, then this is 2 times frequency 1, and this is 3 times the frequency 1. Okay, but they're never going to ask you to work this out, because we can't follow the same equation for the stationary waves on a string, because we don't have any tension here, we don't have any mass per unit length. So our wave speed has to be calculated differently, and we're going to have to look at pressure variations, and it's going to get a lot more complicated. So we just kind of ignore that bit for there. Okay, now the question is, we know we're forming these waves, but usually we would say that sound waves reach our ears because they are progressive waves, because they travel through the air to get to us. So why, if we have stationary waves, can we still hear the sound that's coming out when they're plucking it? And this is because we can still transfer energy using a stationary wave. Okay, so now let's look at how would we transfer energy of a stationary wave. So if we transfer of energy, if I take, I'm going to use a stationary wave on a string just to make it a little bit simpler. So if I take the first harmonic, okay, so I take something that looks like this, fixed at both ends. Let's say this is a guitar string. what it's going to do is vibrate back and forth between these positions, and it will go through every position in between. But what we can also say is that the amplitude is the measure of the power. So the power is still proportional to the amplitude squared, which means the amplitude is where we're actually transferring energy. That's the important point. Okay, the place along a stationary wave that energy is actually transferred is always the antinode. Okay, so the antinode, the larger your antinode, the more energy that you can transfer. Now, obviously, in real life, we don't have an infinite amount of energy, so we're not going to have a stationary wave that lasts forever on a single pluck of a string. Okay, so if we pluck a string in a single time, it will form a stationary wave, but then this antinode, the antinode, dissipates energy. Antinode dissipates energy. What that means is that if it's dissipating it, it is changing. If you imagine all of the air molecules around the guitar string, those things are being pushed, they're being given energy. And when they're pushed and given energy, we form a new sound wave on the outside that's going to move off. So that's how we can hear the sound. Okay, because the antinode dissipates the energy, and we know it's only one pluck of the string, so eventually we're going to have dissipated all of the energy and it comes back to being flat. This is why you can only hold a note on a guitar for so long. It's never going to be you pluck the string and then the note lasts for forever. You'll eventually get zero energy unless you spend a lot of time continually plucking it. You will only get a stationary wave for a few seconds. And we're going to look at how we can get a stationary wave to form properly when we look at the required practical, because you will have to do a required practical that is going to make you calculate the fundamental frequency for a specific string, and then being able to find that using a vibration inducing equipment. Okay. So if we know this idea that the antinode dissipates energy, we can also apply this idea of stationary waves to some other things. We can usually do this with microwaves. Okay, so stationary waves aren't just formed between sound waves and waves on a string, can also form with electromagnetic waves. We can also get microwaves. And the way your microwave works is that inside your microwave, on the side where you have all of your digital buttons and stuff, in the back of there you have a big microwave emitter. You have a microwave emitter, and the size of your microwave is specifically designed so that it can fit one of these harmonics or stationary waves. Wouldn't technically be a harmonic here because we're not producing sound, but it is designed so that we can emit the microwave, and it will do this, and then it will get reflected back, and then you have stationary waves inside of your microwave oven. Okay, so this is how your microwaves work. Obviously, they're not only going to send out one microwave, they'll send out loads of microwaves. But I'm just going to simplify it down to imagine you had one microwave. And so then what happens there is you get these nodes and antinodes. And we know that the antinodes are where the energy is going to be dissipated. So if you have food that is going to be in an antinode, that's going to be the hottest section. If you have food that is centered on a node, you're not actually going to heat that. So this is why sometimes when you put food in the microwave, you get cold spots. That's because that cold spot was actually centered on a node, so no energy is being transferred to it. It's only being transferred to the parts around it. This is also why we have the turntable that spins around to try and get all of the energy to go around, so we never have anything that's centered on a node. is the idea of it. It's obviously not perfect because sometimes you can get nodes that just keep reappearing every time we spin it, and so we're not going to actually have enough time to transfer a lot of energy. But in general, the microwave comes out, gets reflected. We have two progressive waves that are that have the same frequency, and because of that, they will then superpose, form nodes and antinodes, and then we get stationary waves. So this is everything that you're going to need to know about stationary waves. There is also a required practical, but I'm going to make a whole section of these videos just going through each of the required practicals and what you'd need to know about them. So I would go watch that video to go through the required practical. But hopefully all of this makes sense. It is literally just reflecting it, and then it interferes with itself and then forms a stationary wave that is of a certain frequency, and then it can transfer energy out to whatever's around it. Thank you for watching.